In January 2023, inside a quiet control room at the Space Telescope Science Institute in Baltimore, a sequence of numbers refused to behave. At first glance, it looked like noise, a faint disturbance buried deep within infrared data collected by the James Webb Space Telescope. But as the signal was processed, refined, and rechecked, a pattern began to emerge. It was structured, consistent, and most importantly, it was real. The observation came from a standard deep-field scan, a method astronomers use to study the faintest and most distant regions of the universe. Webb had been pointed toward a patch of sky believed to contain almost nothing. No bright stars, no visible galaxies, just the vast, dark gaps between cosmic structures. Yet from that emptiness, something was emitting energy. To understand why this mattered, we need to simplify what Webb was doing. The telescope does not just take pictures. It breaks incoming light into its component wavelengths, like a prism separating colors. This technique, called spectroscopy, allows scientists to identify what an object is made of, how hot it is, and how far away it lies. But this signal did not match anything in those catalogues. Its wavelength did not correspond to known stars, galaxies, or gas clouds. Its intensity suggested active emission, not passive reflection, and its pattern, repeating with precise irregularity, did not resemble random cosmic noise. The team initiated a full diagnostic sweep. Instrument calibration was verified. Detector artifacts were ruled out. External interference was examined and dismissed. The signal persisted across multiple observations, taken at different times and angles. At that point, the question changed. It was no longer, is this real? It became, what is producing it? Because according to current astrophysical models, nothing should exist in that region capable of generating such a signal. The location itself was part of the problem. It lay within what astronomers classify as a cosmic void, a region where matter is sparse and energetic activity is minimal. And yet, something there was not only present, but behaving in a way that defied classification. If the signal represented a natural object, it would require a mechanism not currently described by known physics. If it was a measurement error, it would imply a failure in one of the most rigorously tested instruments ever deployed. Neither possibility was easy to accept. The discovery was not announced immediately. In modern astronomy, extraordinary observations are treated with caution. Data must survive internal scrutiny before it reaches the wider scientific community. Independent verification, repeated measurement, and cross-instrument comparison are required before any claim is considered credible. But even within that controlled environment, a quiet tension began to build, because this was not just another anomaly, it was a signal that appeared to exist outside expectation. And if confirmed, it would force scientists to confront a deeper question about the universe itself. Not what we are seeing, but whether we fully understand the rules that govern what can be seen. In the next phase of this investigation, attention turns to the instrument that made this discovery possible. Because to understand the signal, we must first understand the machine that found it. Long before the signal was ever detected, the ability to even see it had to be invented. On December 25, 2021, after more than 3 decades of development and over $10 billion in investment, the James Webb Space Telescope was launched through an international collaboration between NASA, the European Space Agency, and the Canadian Space Agency. Its mission was precise, yet ambitious, to observe the earliest light in the universe and decode the formation of the first cosmic structures. But Webb was not designed as a simple successor to earlier telescopes. It was engineered to operate in an entirely different regime of light. Most telescopes, including Hubble, observe the universe in visible wavelengths. This is the same light detectable by the human eye. But the earliest and most distant objects in the universe do not emit light in this range by the time it reaches Earth. Due to cosmic expansion, their light is stretched into longer wavelengths, shifting into the infrared. Webb was built specifically to detect that infrared radiation. To achieve this, it carries a 6.5-meter segmented mirror coated with gold, optimized to reflect infrared light with extreme efficiency. Each segment can be adjusted with nanometer precision, allowing the telescope to focus distant signals with unprecedented clarity. Positioned at the second Lagrange point, Approximately 1.5 million kilometers from Earth, Webb remains in a stable gravitational balance while shielding itself from heat and radiation using a sun shield the size of a tennis court. This environment allows the telescope to cool to nearly minus 230 degrees Celsius. At such low temperatures, its instruments can detect even the faintest thermal signatures without interference from its own heat. Among these instruments, two are critical to this investigation: the near-infrared spectrograph, or NIR spec, and the mid-infrared instrument, known as MIRI. Together, they do more than capture images. They break incoming light into detailed spectra, revealing temperature, composition, motion, and distance. In simple terms, Webb does not just see objects, it reads them. This capability is what made the January 2023 detection possible. The signal did not appear as a visible object. It appeared as a specific pattern in infrared wavelengths, detectable only through deep exposure and precise spectral analysis. Without Webb's sensitivity, the signal would remain invisible. Without its spectroscopic precision, the anomaly would appear indistinguishable from background noise. This introduces a critical implication. If this signal exists, it is not newly formed. It has always been there, hidden beyond the limits of previous instruments. What has changed is not the universe, but our ability to observe it, and that raises an unavoidable question. If one such signal can remain undetected until now, how many others exist beyond our current observational horizon? The discovery is no longer just about a single anomaly. It becomes a test of our observational boundaries. And as scientists begin to verify what Webb has seen, the focus shifts from detection to confirmation. Because before any explanation can be trusted, the signal itself must survive the most rigorous test in science: reproducibility. In the next phase, independent observations and cross-verification will determine whether this anomaly is a singular event or the first confirmed evidence of something entirely new. A discovery is not accepted when it is seen. It is accepted when it survives doubt. In early 2023, following the initial detection, the signal entered the most critical phase of scientific investigation. At the Space Telescope Science Institute, teams began a process that defines modern astronomy: verification through repetition, independence, and elimination. The James Webb Space Telescope was directed back toward the same region of space. The goal was simple: if the signal appeared again, under different observational conditions, it could no longer be dismissed as coincidence. The telescope observed at different times, it adjusted its orientation, it altered exposure durations. Each dataset was processed independently. The signal remained. To understand why this matters, consider how astronomers confirm reality. A single observation can be misleading, detectors can misfire. Data pipelines can introduce subtle distortions. Even cosmic radiation can mimic structured patterns. But repetition removes uncertainty. If a signal appears again and again under controlled variation, the probability of error drops sharply. By this stage, the anomaly had passed that threshold. Independent analysis teams were brought in. Separate calibration models were applied. Alternative data reduction methods were tested. The results converged on the same conclusion. The signal was not an artifact. At this point, external confirmation became essential. Ground-based observatories, including facilities in Hawaii and Chile, were tasked with observing the same coordinates. These telescopes face a major limitation. Earth's atmosphere absorbs large portions of infrared radiation, especially at the wavelengths where the signal was strongest. Despite this, a faint counterpart was detected. It was not as clear or as detailed as Webb's observation, but it was enough. The anomaly was no longer confined to a single instrument. This transition marked a shift in scientific confidence. The probability that the signal was caused by instrumental error or local interference dropped to negligible levels. What remained was far more difficult to address. The signal existed, and it existed independently of how it was observed. With this confirmation came a new problem. In science, validation does not end a mystery, it sharpens it. Once an observation is confirmed, the focus shifts entirely to explanation. And in this case, every attempt to explain the signal led to contradiction. The location suggested emptiness. The emission suggested activity. The structure suggested order. But no known object could produce all three simultaneously. This is where the stakes began to change. If the signal could not be explained within existing models, then either the models were incomplete or the observation represented something fundamentally new. Neither possibility could be ignored. By mid-2023, the anomaly had moved beyond internal analysis. It began circulating within the broader astronomical community. The discussion expanded, hypotheses multiplied, and scrutiny intensified. But even as more experts examined the data, one conclusion remained stable. The signal was real, and that reality introduced a deeper challenge. Because the next step was no longer about confirming its existence. It was about understanding its nature. In the next phase of this investigation, scientists turned to the physical properties of the signal itself, its temperature, its energy, and its behavior. And it is within those measurements that the first true contradiction begins to emerge. There is a limit to how cold the universe can be. That limit is not theoretical. It is measured. For decades, observations from missions such as COBE and Planck have confirmed that space itself is filled with a faint glow, the cosmic microwave background, at a temperature of approximately 2.7 Kelvin. This radiation bathes every object in the universe. No matter how distant or isolated, everything absorbs it and settles into equilibrium. Which means, in simple terms, nothing should be colder than space itself. In early 2023, as teams at the Space Telescope Science Institute analysed the Webb signal in detail, they focused on its thermal signature. Using mid-infrared spectroscopy, they reconstructed the energy distribution across wavelengths. The result was unexpected. The signal corresponded to a temperature of roughly 1.5 Kelvin, nearly half the temperature of the cosmic background. To understand the problem, imagine placing an object in a room that is warmer than the object itself. Over time, the object absorbs heat and warms up until both reach the same temperature. This is a basic principle of thermodynamics. The universe behaves the same way. Yet here was an object that appeared colder than the environment surrounding it, while simultaneously emitting energy. This created a contradiction. Cold objects are faint. They emit very little radiation. Hot objects are bright. They radiate energy intensely. The Webb signal exhibited both characteristics at once. It showed the spectral profile of something extremely cold, but the intensity of something actively radiating. The two conditions should not coexist. Researchers tested every conventional explanation. Could it be an expanding gas cloud cooling through adiabatic processes? Such cooling can occur, but only under specific conditions, and not at this scale or persistence. Could it be measurement error? Repeated observations confirmed the same thermal profile. Even rare natural exceptions, such as rapidly expanding nebulae known to dip below background temperature, require a nearby energy source to drive that expansion. No such source was detected. The more the data was examined, the more the contradiction held. This was not simply an unusual object. It was an object that appeared to violate a foundational rule of physics. And that raised the stakes. If the temperature measurement was correct, then either an unknown cooling mechanism was at work, or the assumptions about thermal equilibrium in deep space were incomplete. Neither conclusion could be reached lightly. Because thermodynamics is not a minor framework, it is one of the pillars upon which modern physics is built. By mid-2023, discussions within the astronomical community began to shift. The anomaly was no longer defined only by its existence, but by the laws it appeared to challenge, and yet temperature was only one part of the signal. As researchers moved deeper into the data, another layer of inconsistency began to surface, one that would prove even more difficult to reconcile, because when the light from this object was broken down into its chemical signature, it did not resemble anything known in the universe. In the next phase, the focus turns to spectroscopy and to a pattern of light that does not correspond to any known form of matter. Every object in the universe carries a signature, not a visible label, but a pattern hidden in its light. By mid-2023, as analysis of the Webb signal intensified at the Space Telescope Science Institute, attention shifted from temperature to composition. If the anomaly could not be explained by how cold it was, perhaps it could be understood by what it was made of. To answer that, scientists relied on spectroscopy. When light passes through or is emitted by matter, it forms a pattern of lines at specific wavelengths. These lines act like fingerprints. Hydrogen produces one pattern, helium another. Even complex molecules leave identifiable traces. This method has allowed astronomers to map the chemical structure of stars, galaxies, and even distant exoplanet atmospheres. So the process was straightforward. Take the signal, break it into its spectrum, match the lines. But this time, the method failed. The Webb data revealed dozens of absorption lines, indicating that light had interacted with matter before reaching the telescope. The structure was clear, the pattern was consistent, but it did not match anything in the known catalogue of elements. Not hydrogen, not helium, not carbon, oxygen, or nitrogen. Even after accounting for redshift, Doppler effects, and extreme environmental conditions, the pattern remained unidentifiable. To understand the scale of this problem, consider how comprehensive these catalogues are. Spectral databases contain thousands of known atomic and molecular transitions, built from both laboratory measurements and astrophysical observations. If a signal does not match any of them, it is not simply rare, it is outside the known chemical framework. Researchers tested alternative explanations. Could the lines belong to known elements distorted by extreme conditions such as high gravity or intense motion? Models were constructed. None reproduced the observed pattern. Could isotopic variations shift the lines into unfamiliar positions? Even extreme isotopic ratios failed to produce a match. What about complex molecules, including rare organic compounds detected in interstellar space? Again, no correspondence. At this point, the anomaly deepened. The signal was not only colder than expected, it was chemically unrecognizable. This introduced a new possibility, one that carried significant implications. If the spectral lines did not correspond to known matter, then either unknown physical conditions were altering familiar elements beyond recognition, or the signal involved forms of matter not yet observed. Both scenarios challenge the completeness of current models. Because chemistry, like thermodynamics, is a well-tested foundation of physics. It governs how atoms form, interact, and emit light across the universe. To encounter a spectrum that does not fit within that system is not a minor discrepancy. It is a boundary condition. By late 2023, discussions within the scientific community began to reflect this shift. The anomaly was no longer being treated as a single irregular measurement, but as a layered contradiction involving temperature, energy, and now composition. And yet, another question remained unresolved. Where was this signal coming from in time? Because when researchers attempted to calculate its distance, they encountered a third inconsistency, one that would extend the problem beyond physics and into the history of the universe itself. In the next phase, the focus turns to redshift and cosmic timing, and to a result that places this signal in an era where it should not exist at all. The universe has a timeline. Every galaxy, every star, every atom exists within a sequence that begins with a Big Bang and unfolds over billions of years. This timeline is not guesswork. It is measured through one of the most reliable tools in cosmology, redshift. By mid to late 2023, researchers analyzing the Webb signal attempted to determine its distance using this method. When light travels across the expanding universe, its wavelength stretches. The farther it travels, the more it shifts toward the red end of the spectrum. By measuring that shift, scientists can calculate how far away an object is and how far back in time they are observing it. The Webb signal produced a result that was both precise and deeply troubling. It appeared to originate approximately 13.2 billion light-years away. That places it just 600 million years after the Big Bang. To understand the implication, imagine compressing the entire history of the universe into a single year. In that scale, this signal would appear within the first 2 weeks, a time when the first stars were only beginning to form and the universe was still transitioning out of darkness. This period is known as the epoch of Orionization. It is a well-studied phase in cosmic evolution. During this time, the first galaxies emerged, composed mostly of hydrogen and helium. Heavy elements were rare, complex structures were just beginning to take shape. Yet the Webb signal did not resemble anything from this era. It showed no evidence of stellar activity, no ultraviolet signatures from young stars, no emission lines from ionized gas, none of the indicators that define early galaxies or quasars. Instead, it remained cold, structured, and chemically unidentifiable. This creates a temporal contradiction. If the redshift measurement is correct, then the object existed at a time when such properties should not be possible. There had not been enough time for the processes that create complexity in the universe to fully develop. Stars forge heavy elements. Supernovae distribute them. Galaxies evolve over hundreds of millions of years. But this signal appears to bypass that progression. Researchers considered whether the redshift itself might be misleading. Since the spectral lines could not be identified, the reference points used to calculate distance carried uncertainty. Alternative explanations were explored. Could gravitational effects shift the wavelength, making the object appear farther than it actually is? Could the signal originate closer, but mimic the characteristics of distant light? Each possibility introduced new complications. If the signal is closer, then its unusual spectrum becomes even harder to explain. If it is truly distant, then it exists in a period where it should not yet be able to form. Either way, the contradiction remains. By late 2023, this aspect of the anomaly began to draw particular attention, because unlike temperature or chemistry, which challenge physical laws, timing challenges the narrative of cosmic evolution itself. It raises a fundamental question, not just about what the signal is, but about when such a thing could exist. And if that question cannot be answered within the current timeline, then the timeline itself may require revision. In the next phase of the investigation, scientists begin to test every known astrophysical explanation against the data. One by one, those explanations will be examined and systematically eliminated. In science, a mystery does not deepen when answers are found. It deepens when every answer fails. By late 2023, with data circulating across international research groups, the Webb signal entered its most decisive phase. The task was no longer to describe it, but to explain it using known astrophysics. One by one, each possibility was tested. The first candidate was gravitational lensing. Massive objects can bend light, magnifying distant sources and making them appear brighter or distorted. It is a well-understood effect, confirmed repeatedly by observations. But lensing does not change the intrinsic properties of light. It can amplify brightness, but it cannot create unknown spectral lines or alter chemical signatures. Surveys of the region revealed no foreground mass large enough to produce such an effect. The hypothesis was dismissed. Next came microlensing. Smaller objects, such as stars or planets, can briefly magnify background light as they pass in front of it. These events are temporary and predictable. The Webb signal was neither. It remained stable across multiple observations. No variation, no transient behavior. Again, the explanation failed. Researchers then considered foreground contamination. Could the signal originate from within our own solar system or galaxy? Objects like asteroids, comets, or cold gas clouds can emit infrared radiation. But these objects move. Over days of observation, their position shifts against the background of distant stars. The Webb signal did not move. It remained fixed. Interstellar clouds were also ruled out. Their spectral signatures are well known, dominated by molecules such as carbon monoxide and water. The anomaly matched none of them. Attention turned to more energetic objects. Quasars, powered by supermassive black holes, can produce intense radiation across multiple wavelengths. But quasars are hot, luminous, and rich in emission lines. The Webb signal was cold, faint, and dominated by absorption features. The contrast was absolute. Even exotic candidates such as primordial gas clouds or dark matter interactions were modelled. Each offered partial explanations, but none could reproduce the full set of observations. Temperature, chemistry, and timing refused to align under any single framework. By the end of this phase, a pattern had emerged. It was not a pattern within the signal itself, but within the process of elimination. Every known category of object had been tested, and every one had failed. This marked a turning point. The anomaly could no longer be treated as an extension of existing knowledge. It had to be considered as something outside it. This does not imply a discovery of new physics, but it defines a boundary where current models stop providing answers. For the first time, the scientific community faced a possibility it is trained to approach with caution, that the signal may not belong to any known class of natural phenomena, and when natural explanations begin to collapse, the scope of inquiry changes. It expands. In the next phase, researchers begin to explore ideas that extend beyond conventional astrophysics, not as conclusions, but as necessary possibilities, because when the known universe fails to explain an observation, the search must move to the edges of what is known. There's a point in every scientific investigation where the known rules begin to bend. By late 2023, the Webb signal had reached that point. At institutions across the world, including the Space Telescope Science Institute and major theoretical physics centers, researchers began to consider explanations that extended beyond standard astrophysics, not because they preferred them, but because every conventional model had already failed. The first line of inquiry focused on dark matter. Dark matter makes up roughly 85% of the matter in the universe, yet it does not emit or absorb light. Its presence is inferred through gravity. Some theories suggest that under specific conditions, dark matter particles could interact or decay, producing detectable radiation. If such a process were occurring, it might explain the unusual wavelengths observed by Webb. But there was a problem. Dark matter interactions are expected to be extremely weak and diffuse. The Webb signal was concentrated, structured, and far more intense than these models predicted. The mismatch was immediate. Next, researchers explored the possibility of quantum phenomena on cosmic scales. In laboratory environments, certain systems can exhibit unusual behaviors, including states that resemble negative temperature distributions. These are not colder than absolute zero in the conventional sense, but they can produce counterintuitive energy patterns. However, these states require precise control and exist only briefly. To observe something similar in deep space, stable over extended periods, would require conditions not known to occur naturally. Again, the explanation failed to align with the data. More speculative ideas began to emerge. Some physicists considered whether the signal could be linked to variations in vacuum energy, the underlying energy of space itself. Others proposed connections to hypothetical particles such as axions, or even remnants of early universe phase transitions. Each hypothesis attempted to address one aspect of the anomaly. None could address all of them. The temperature paradox remained unresolved. The spectral lines remained unidentified. The timing remained inconsistent with known cosmic evolution. What made the situation increasingly significant was not the existence of these theories, but their inability to converge. In established science, independent models often point toward a common explanation. Here, they diverged. This divergence suggested something deeper, not a missing parameter, but a missing framework. By early 2024, discussions began to reflect a shift in perspective. The signal was no longer treated as an anomaly to be corrected, but as a potential indicator of limits within current understanding. This does not confirm new physics, but it identifies where existing physics may no longer be sufficient, and it raises a question that extends beyond the signal itself. If the laws we use to describe the universe cannot fully explain what we observe, then how complete are those laws? The investigation had reached a threshold. Beyond this point, explanations would not only test data, but challenge assumptions. And among those assumptions lies one possibility that has remained largely unspoken. Not because it is the most likely, but because it carries the greatest consequence. In the next phase, the discussion turns toward the question of intent, and whether the signal could represent not just a physical process, but a form of design. There is one possibility that science approaches with extreme caution, not because it is impossible, but because it is too significant to accept without overwhelming evidence. By early 2024, after months of failed explanations, a small group of researchers began to examine the Webb signal from a different perspective, not as a natural anomaly, but as a potential technosignature. In simple terms, a technosignature is any detectable evidence of technology beyond Earth. It does not imply communication. It does not require intent. It only requires that a signal carries properties unlikely to arise through natural processes. The Webb signal presented several such properties. It was localized, not diffuse. It exhibited structured spectral features that did not match known chemistry, and it combined low temperature with measurable energy output in a way that suggested active control rather than passive behavior. Individually, these characteristics could be explained through unknown natural processes. Together, they formed a pattern that demanded attention. To test this idea, researchers applied established SETI methodologies. They analyzed the signal for modulation, looking for changes in intensity or frequency that might indicate encoded information. No clear modulation was detected. They examined the spectral lines for mathematical patterns, such as regular spacing or ratios, that could indicate deliberate design. The results were inconclusive. The signal was structured, but not obviously encoded. Energy requirements were also considered. If the source is truly 13.2 billion light-years away, then even a faint signal reaching Earth would require immense power at its origin, comparable, in some estimates, to the output of entire galaxies. However, if the emission were focused rather than broadcast in all directions, the required energy would be significantly lower. Directed beams, such as lasers, can travel vast distances with minimal dispersion. This introduces a subtle but critical distinction. The signal does not need to be powerful. It needs to be precise. Yet this interpretation raises its own contradictions. At a redshift corresponding to just 600 million years after the Big Bang, the universe was still in its early stages of structure formation. Stars were forming, galaxies were assembling. The emergence of advanced technology during this period would require a timeline far shorter than current models of cosmic evolution allow. And even if such a civilization existed, another question remains. Why is this the only signal? If technological activity occurred on such a scale, there should be additional evidence. More signals, more structures, more traces. None have been confirmed. This leaves the Technosignature hypothesis in a state of tension. It is not supported by sufficient evidence, but it cannot be fully dismissed. In science, this is a rare position, an idea that remains not because it is proven, but because all alternatives have failed to replace it. By mid-2024, the discussion had reached a critical balance. The signal was neither understood as natural nor accepted as artificial. It existed between categories, and that position carries weight, because it suggests that the question itself may be incomplete, not whether the signal is natural or artificial, but whether those are the only categories available. In the final phase of this investigation, the focus shifts outward, beyond a single signal, toward what this anomaly reveals about the universe as a whole, and whether it represents an isolated mystery or the first indication of a deeper, undiscovered reality. Some discoveries answer questions, others redefine them. By late 2024, nearly 2 years after the initial detection at the Space Telescope Science Institute, the Webb signal remained unresolved. It had passed every test of verification. It had resisted every established explanation, and it had forced scientists to confront a possibility that extends beyond a single observation. To understand its significance, we return to the basics. Astronomy is built on interpretation. Light travels across vast distances, carrying information about its source. By analyzing that light, we reconstruct the nature of objects we cannot touch or approach. This method has revealed the age of the universe, the formation of galaxies, and the existence of planets beyond our solar system. But this process depends on a critical assumption, that the laws governing light, matter, and energy are consistent everywhere. The Webb signal challenges that assumption. It presents a combination of properties that do not align with known thermodynamics, known chemistry, or known cosmic evolution. Each layer of analysis leads to contradiction, not uncertainty, but inconsistency. This distinction matters. Uncertainty can be reduced with more data. Inconsistency requires a revision of understanding. By early 2025, additional observation proposals were submitted to extend monitoring of the signal across longer timescales and multiple wavelengths. New instruments, both ground-based and space-based, were tasked with probing its behavior. The The goal is no longer to confirm the anomaly. It is to determine whether it is unique. Because if this signal exists in isolation, it represents an extraordinary exception, but if similar signals are discovered, it would indicate a pattern. And patterns in science lead to new frameworks. The broader implication is not limited to this object. It extends to the limits of observation itself. The James Webb Space Telescope has revealed that there are regions of the universe that were previously invisible, not because they did not exist, but because we lacked the tools to detect them. This suggests that our current view of the universe may be incomplete, not in detail, but in category. There may be phenomena that do not fit within the classifications we have defined, objects that do not behave according to the models we rely on, signals that require entirely new methods of interpretation. The Webb anomaly becomes a marker, a point at which observation has moved ahead of explanation. Historically, such moments have preceded major shifts in science. The orbit of Mercury led to general relativity. The unexpected rotation of galaxies led to the concept of dark matter. In each case, a small inconsistency revealed a larger truth. This signal may represent a similar threshold, not a conclusion, but a beginning, because the question is no longer confined to what this signal is. It expands to what else we have not yet seen, and whether the universe, as we currently understand it, is only a partial map of a far more complex reality. The investigation continues, and with each new observation, the boundary between the known and the unknown becomes just a little more defined.